Step 6, section 2, please. How likely or unlikely an event is to occur is the definition of our idea of probability. So if I've got this giant collection of things that could occur, I want to ask how likely is some particular thing occur? Some terminology. An experiment is a process whose outcome is unknown. And for us, we're thinking of experiments whose outcome is from some collection of possible things. That collection is called a sample space. Our goal is to think of this as a finite set. An event is some subset of the sample space. So I do this experiment. It could be fairly simple. Here's my experiment. I flip the coin. You have no idea what's going on here. But there's a finite collection of outcomes in my experiment available to me. It is possible to deal with infinite sets, whether those are countably infinite or uncountably infinite. But when our sample space is infinite, we're usually talking about continuous probability. I'll save that for Calc 2. If my sample space is a non-empty set and all of the outcomes are equally likely, in our sample space, then for any event in our sample space, the probability of that event is a counting argument. All I have to do is make a fraction. How many ways does the thing I want to have happen? Divided by how many total ways are there? This is a critical piece of that. I must have equally likely outcomes. So that's going to mean something specific. But let's start with something easy. Here's a deck of cards. Pick a card, right? You know what a standard deck of cards looks like? How many ways can you pick a queen? And there are 4 queens in the deck. There are 52 cards. So if I say pick a card as my experiment, my sample space has 52 things in it. I want to know the probability of getting a queen. Well, then my event, the number of ways to get a queen, is 4. So the probability of getting a queen is 4 out of 52, or 1 out of 13. You're welcome to give me a decimal. I don't care. Same question, pick a card. What is the probability you picked a club? Say it again. 13 out of 52, because there are 13 clubs. And again, you could simplify that fraction or give me a decimal if you want. That's fine. Here's my next experiment. Roll 2 6-sided dice, 2d6. What is the chance you roll an odd total? Here are my 2 dice. Total's 10. Total's 4. What's the chance I roll an odd total? Well, now building my sample space and my event is an enumeration. How many possible outcomes are there for rolling 2 6-sided dice? There are 12 possible totals. Actually, there aren't 12 possible totals. There are only 11 possible totals. You can't roll a 1. But you can get 2 through a 12, right? That's only 11 possibilities. But those are the totals. That's not the actual outcomes. I'm rolling 2 dice, yes? I go back to last chapter. Let's count. How many ways can I have 2 dice come up? Because there are 6 options here and 6 options here. And then I can go through and actually enumerate them all. And the reason I need to enumerate them all is because I then need to add them up and see how many are odd and how many are even, right? So I need to actually build the sample space. So I'm just going to make a chart. You could make a tree, couldn't you? You could make a tree diagram here. First die followed by second die. I'm going to make it as a table. Options, for the first die, options for the second die. Yes? And on I go. First, a 1 followed by a 1, a 1 followed by a 2, a 1 followed by a 3. Notice I'm putting the first die first, the second die second. I'm going to be here for a minute. Wasn't short to write out the entire sample space here. But now I can go through and I can say, okay, add the numbers. Which of these have a total that's odd? And now I can count my events. If my event E is that the total of my dice is odd, how many underlines are there? So the probability of this event is 18 out of 36. Or 1/2.
Could you also just tell me, like adding up, how many ones that only have one on them? We are.
Yeah, because of parity, right? If I have one odd number, and that's really all I did is I underlined the 3 in the first row where 1 is odd and 1 is even. In the second row, 1 is odd and 1 is even. I just underlined all of those things. But I can also think of it the other way. If the first number is odd and the second number is even, it's going to count. If the first number is even and the second number is odd. So I have to go through and look at my tree diagram and label out all the branches that count. Same idea, isn't it? But now I can say the reason I used this table instead of the list 2 through 12, right? Because if you add the numbers and you're looking at the total, the totals are either 2 or 3 or 4 or 5 or 6, all the way up to 12. That's the best I can do on 2d6. So why not just use this list instead of this list? Well, here's where our definition comes back into play. In order to use this counting argument, I need to have equally likely outcomes. Looking at this table, tell me, what's the chance you roll a total of 2? There's only one way to do it. Snake eyes. On the other hand, what's the chance you roll a total of 4? There are 3 options that come up to a 4. As a matter of fact, that tells me that these outcomes are not equally likely. And so I couldn't just count these outcomes. If I just counted these outcomes, I'd get 6 out of 11 that are, sorry, yeah, 6 out of 11, right? Yeah. 1, 2, 3, 4, 5 out of 11. Only 5 that are off. And that's not 50%. But when I count it this way, it is 50%. So the way I choose to count is based on whether or not I know those outcomes to be equally likely. Questions? My sample space could get huge. One of my favorite games at my in-laws' house is Yahtzee, which requires 5 dice. How many outcomes are there? Hey, pair of 3s.
7,770.
6 times 6 times 6 times 6 times 6, 7,776 outcomes. I don't want to make a table. It isn't worth it. So there should ideally be more counting strategies here. We counted card hands, didn't we? On Monday? How many ways are there to get a royal flush? 4. Out of 2,598,960 possible 5-card hands, I know the chance. It's really small, but I know the chance. But if I can count my outcomes in that fashion, using my combinations and my counting of card options or counting of dice options, I can get a better handle on what's going on. Questions? Please notice, for every probability we come up with, the number that represents our probability must be between 0 and 1. Why? That's what this sentence says, Colin. I can't have less than a 0% chance of something happening. I can have more than 100% chance of happening. That's what this sentence is. Why is that true? This is another case in math where you're like, well, duh, isn't it obvious? And the answer is, that's why we prove things in the first place. So there's got to be a proof here somewhere. There's got to be a reason why I know this is true. Why can I never have a probability bigger than 100%? Aha. Remember, our event is a subset of the sample space. If this number were bigger than 1, it means the top is bigger than the bottom. It means a subset is bigger than the whole set. That doesn't cut it because our set is finite. This is why I left off infinities here, because infinity is with that idea, and I don't want to do that. In finite sets, a subset can never be larger than the original set. So that tells me why it can't be bigger than 1. Why can't it be smaller than 0? If there are no options in my event, then my probability would be exactly 0. If I roll a 13 on 2 dice, How can I get a 13? Doesn't work that way, does it? There are no events that total to 13. Then the top of my fraction is 0. Why can't it be less than 0? Huh? My quantity of events would be negative. We're counting things. You don't count starting at the negatives, right? Counting numbers start with 0. So the smallest my E can be is an empty set, which would give me no options. By the way, those of you that like the Avengers or the Marvel Universe, why is Odin king of heaven? Norse mythology is a wonderful thing. They played dice to see who would win heaven, Asgard versus Niflheim versus the Middle Marches. Who would win which kingdom? And Hell picked up the dice and rolled a 12. Said, I'm going to win. And Odin picked up the dice and threw it against the wall so hard that one of them landed 6, the other one broke in half, landed 6-1. He rolled a 13. I didn't pick 13 out of nothing. No matter what the size of my event is, or the size of my sample space, as long as I can count them, I can work this out. Let's play the lottery. What are the rules for playing Powerball? I didn't expect you to know. Get online. The website is powerball.com. It'll tell you all the things you need to know to fill out a ticket. Okay, but there's a little bit more. Pick 5 numbers from, okay, and those are the white balls.
Then 1 to 26.
1 to what?
26.
So I have to actually pick 6 numbers to play a Powerball ticket. I go out and I buy a Powerball ticket. What's my chance of winning? I bought 1 ticket, so my chance is 1 in something. What's the something? Say again? 69 to the power 5 times 26 to the power 1. Unfortunately, no. Because what that would mean is I'd be picking 5 numbers, right? These are the white balls, and then over here I'll put the red ball. If there are 69 options here, how many options are there here? No, because when I draw a ball, it comes out of the pile. I only get 1 chance at that number. So whether that 5 comes up first or second or third or fourth, if a 5 shows up and that's one of my numbers, I'm happy. So really, this is not independent choices. It's not like there are 5 different tanks of balls and I pick from the first tank, the second tank, the third tank. The weekly number does that. I actually pick all 5 balls at once. Okay?
Was it 69 times 68 times?
Again, almost. I pick them all at once. I'm doing this with my hands on purpose. Give me the letter. This is a combination because the order of the numbers coming out doesn't matter. If that 5 comes out first, second, third, it doesn't matter. If it's one of my numbers, I still count. Doesn't matter where it is. So the order doesn't matter. And I'm not allowed to repeat numbers. This is a combination. So instead of having 69 to the 5th, I have 69C5. What about the other ball? What about the red ball? There's only 26 chances, right? 26 to the first is right, but there's only one shot. I could think of this as 26C1, but that's the same as 26. Which is, by the way, the same as 26P1. If I'm only picking one thing, the order in which I pick it doesn't matter. What do I do with these two numbers? Because I have to pick the white balls and the red ball. The word "and" means multiply. By the way, this is not a small number. 11,238,513 times 26 is 292,201,338 possible lottery tickets in the Powerball. My chance is 1 in 292 million. Somebody do me a favor. Go to the National Weather Service website and look up the chance of getting struck by lightning. So I am more than 300 times more likely to get struck by lightning than I am to win the Powerball. Yikes. Now, this idea about whether or not I can repeat objects or not, I can think about this even if I go back to a deck of cards, right? If I said pick a card, and then I said pick a second card, well, what do you do with the first one? There are two options, and we call this idea either drawing with replacement or drawing without replacement. If I think of drawing with replacement, I take a card and then I put it back and I take another card, which means it's possible I could get the same card twice, isn't it? It's almost like they're two separate decks and I pick a card from over here and a card from over here. But if I draw without replacement, then I don't put the first one back. And that changes the number of options in the next step, doesn't it? So, I'm going to ask you to pick two cards from a deck. What is the chance you get two aces? There are two different options depending on which way I do this. So let's think about this. If I draw with replacement, then I can think of this one card at a time. I grab my first card. What's the chance it's an ace? Say again. How many aces are in the deck? There are 4 of them, right? So I count the number of aces for the first card. 4 aces out of 52. And second card. It's like I have a brand new deck. How many aces are in the deck now? There are still 4 because I put the card back. So that changes the way we do this. And so my answer is whatever 16 over 52 squared is. 52 squared. 25, 50 squared is 25. So 2704. Who's got a calculator? It's 52 squared. $2,704. Great. What if I don't replace the card? Well, now I have 2 different ways of looking at this. I could look at it just like this, 1 card at a time. So let's think about what happens. First card, then second card. I pick a card. What's the chance it's an ace? 4 out of 52. With that card in my hand, I pick another card.
3 out of 50.
3 out of 51. So there's 1 fewer card in the deck. It's in my hand. But this, by the way, is 12 over 2652. But somebody give me 2 suits. Those are my 2 aces. Which 2 aces did I get? Hearts and diamonds. I got the 2 red aces. Which one did I get first? If I got the ace of hearts before the ace of diamonds, or I got the ace of diamonds before the ace of hearts, does it matter? So those are equivalent, aren't they? What do I need to do here? To account for those equivalent options, what do I need to do? I need to divide. I need to divide by the number of ways I could rearrange my cards. I need to divide by 2. If I divide by 2, I get 6 out of 2652. I don't like this version. Thinking of that reordering bothers me. I wish I could just take the order and throw. Wait a minute. Wait a minute. I can get the cards in 2 different orders. That not only happens here at the top, doesn't it also happen at the bottom? Which means I really had the same number. I need to divide both of those by 2. Remembering to do this part where I split the order like this bugs me. I want to get rid of the idea of doing order in the first place. So let's not think of drawing 2 cards, one after the other. Let's think of reaching into the deck once and pulling out 2 cards. I'm going to count my options differently. How many ways can I get 2 cards out of the deck? Any 2 cards? $52C2. Now, how many aces are there? There are only 4. How many ways can I get 2 of those 4 aces? Out of the 4 items, I want 2 of them. So the probability of getting 2 aces is 4C2 over 52C2. Grab your calculators. What's 52C2? I like this version much better. Don't think of them as 1 card at a time. Think of it as reaching and grabbing all the cards at once, however many you need. This, by the way, is the same way we counted when we counted how many ways to get 1 pair, right? I got 5 cards. I got 2 of them that matched, and then I got 3 that didn't match, and I just multiplied because I didn't care what the order was. And I used combinations at every step in that to avoid using the order. Questions? Whoops. I have repeatedly multiplied when I saw the word and. That was what we were doing when we were counting things in sets. That was what we were doing with our combination and our permutations and our multiplication principle. So let's go back to the homework I just handed you back from chapter 6, section 1, with all of those counting theorems in there. What do I do when I see that word? I add. And I subtract things that are double counted, right? So if I want to think about 2 events, let's suppose I have 2 events, event 1 or event 2. I even used the union symbol from our set notation. How many things? That looks like a new, sorry. How many things in this union of 2 sets? Oh, to count the number of things here, I count the number of things in set 1. I add the number of things in set 2. And then what do I subtract? What's in both? Now take this entire equation and divide by the size of your sample space. I just turned all those counting things into probabilities. The probability of event 1 or event 2 is the probability of event 1 plus the probability of event 2 minus the probability of being in both. I tell you to pick a card from the deck. What is the chance that you pick a queen or a club? How many queens in the deck? How many clubs in the deck? How many both? The queen of clubs, right? So the chance is probability of a queen plus the probability of a club minus the probability of both. It is possible that this part will be empty, like our sets are disjoint. If our sets E1 and E2 are disjoint, then the events are called mutually exclusive. They can't both happen together. I'm going to roll 2 dice and add the spots. If you play craps, the most common 2 dice game played, you roll 2 dice. If you roll a 2, a 3, or a 12 on your very first roll, you lose. Chance you lose on your first throw. Advantage. None of these things can have any overlap. If you roll a 2, you can't possibly roll a 3 at the same time. If you roll a 3, you can't roll a 12 at the same time, right? There's only one of these outcomes that's possible at any given time. There's no overlap in any of them. So this becomes the chance for 2 plus the chance for 3 plus the chance for 12, since there is no overlap. They're exclusive to one another. Which means I go back to that big 6 by 6 grid and I count. There's one way to get a 2. There's 2 ways to get a 3. And there's one way to get a 12. So your chance of losing the first throw is 1 in 9, 4 out of 36. You win on your first throw if you roll a 7 or an 11. So there's more chance of winning than there is of losing on your first throw. But notice that left a bunch of options out, right? If you roll anything other than one of those 5 numbers, then you have to roll that again before rolling a winning number to win. You've made a point, and you have to remake the point to go back to the game over. Craps is a complicated game. What does the word not tell me to do when I'm counting? And count everything else, right? If the complement of an event is everything that isn't in it, then the probability of not my event E, that's the chance of E complement, is the same as the chance of S minus E. Wait a minute. The chance of something happening is, I do my experiment. What's the chance something happens? 100%. So what's the chance it's not in this set E, it's all of the rest of the chance, isn't it? If there's a 4 in 36 chance I roll a 2, 3, or a 12, then there's a 32 in 36 chance I roll one of the other numbers. Because those are all the outcomes that could happen. It is sometimes easier to count complements. I'm back to playing poker again. I get 5 cards. What is the chance at least one of them is an ace? Well, there's a problem here. I could get 1 ace, I could get 2, I could get 3, I could get 4. I'm only playing with 1 deck, so I can't get 5. That's a lot of different outcomes to count, isn't it? What can't happen? What's the complement of this event? Getting 0 aces. And there's only one option to do that, where none of the cards are aces, right? That makes my life a lot easier to count. So if I were to say what I really want to do is count no aces, that's easier to count. If I'm going to get no aces out of my 52C5 options, because that's the number of ways I get 5 cards, if none of the aces are allowed to end up in my hands, how many cards do I have to pick from? 3. Because the rest of the aces are somewhere else. I don't get it. So I'm going to get 5 cards, but they're going to come from the other 48 cards in the deck. And that means, by the way, I can work this out. These numbers are off my calculator. Let's see, 2, 5, 9, 8, 9, 6, 0. The top one is 1, 7, 1, 2, 3, 0, 4. Or roughly 0.639. I wrote them down already. So the chance of getting at least 1 ace is 1 minus the chance of getting no aces. 1 minus 0.639 is roughly not 639, 659. I can read my own handwriting, 0.341. There were fewer options to count here, rather than counting 1 ace or 2 aces or 3 aces or 4 aces. I just counted 1 ace, 1 option, no aces. By the way, I can put this together with my tree diagrams. I want to look at options, but the options have different probabilities. I could make a tree diagram. And then I could put a probability on each branch. How many of you know the Monty Hall problem? The game show, The Price is Right? I am going to make you a deal. Pick a door. There are 3 doors behind me. Door 1, door 2, and door 3. You can pick any of them at all. Behind 2 of these doors is a pile of garbage. Behind 1 is a car. Brand new, whatever car you want. You pick a door. I open one you didn't pick and show you a pile of garbage. Now you have a choice. Keep the door you already picked or switch doors. which is a better chance of you winning the car? There's a lot to be thought about what the branching that comes after here. If the car is behind door 1 and you picked that door, then I can either open door 2 or door 3. I have information you don't, right? If the car is, I can do that. And that means the chance of me opening door 2 when the car is behind door 1 is 1/3 times 1/2. Follow the branches and multiply. Follow the branches and multiply. You picked door 2. Car's in door 1. I have to open door 3 to show you a pile of garbage, don't I? That's a guaranteed to happen. Chance is 100%. Same thing here. I have to open door 2. The outcomes aren't equally likely, are they? And so by adding the probability to each of my outcomes, I can map my way through the probabilities. These, by the way, are called joint probabilities and conditional probabilities. More on that in your prob and stats class. There are lots of really, really interesting things that come out of this. You should actually look up the Monty Hall paradox to see about this. Mythbusters actually ran the experiment. Simulated 1,000 car door choices with a physical set of doors. Go watch the episode. About 20 minutes. It's amusing as hell. I will see you all on Friday.